Let's start with a traditional neural network. It has an input layer, hidden layer, and an output layer. Information flows in only one direction from input through the hidden layers to the output. But this design has a key limitation. It has no memory. Each input is processed independently, so it can't remember past information. To solve this, we use a recurrent neural network or RNN. RNNs are designed to work with sequences. This shows the previous timestamp t-1, the current step t, and the next step t+1. At each time step, the network receives an input like X and produce an output Y. But there is the magic. The RNN also passes information from one step to the next. This is called the hidden state, labeled as H. This hidden state is the RNN's memory. Watch the flow. At the first step, an input X0 is processed. It produces an output Y0, but also a hidden state H. That gets passed to the next step. At time t, the cell processes both the new input x1 and the hidden state from the previous step. This is how the context is carried forward. What are RNNs great for? They are perfect for processing any kind of sequential data. This includes text, where the order of the words matter, audio, which is the sequence of sound waves over time, and even video, which is sequence of frames. The main takeaway is if your data is sequence where order is important, an RNN is a powerful tool. Let's look at a concrete example, which is a text prediction. Imagine we want to train an RNN to predict the next letter in a word. We feed it the word hello, one letter at a time. First we input H. The RNN processes it, predicts the next letter E, and passes its hidden state, its memory of seeing H, to the next cell. Now we input E. The second cell uses the E and the memory of H to make the prediction, L. It then passes the new hidden state forward. This continues for each letter. The network uses the current letter and all the context from the past letters stored in the hidden state to make its next prediction. This continuous flow of memory is what allows the RNN to understand the context of the entire sequence. But the simple design has a major challenge. What happens with very long sequence? Imagine processing a long sequence sentence. To learn, the network has to send an error signal backward through time from the end of the sequence all the way to the beginning. This can cause the signal to get weaker and weaker, effectively disappearing by the time it reaches the beginning. This is famously known as the vanishing gradient problem. Here's why mathematically the gradient, that learning signal, is calculated as a long chain of multiplication. We are multiplying many small numbers together, one for each time step. And if you repeatedly multiply numbers that are less than 1, the final result gets exponentially smaller, approaching 0. The gradient vanishes. This means the network can't learn from the early parts of the sequence. The solution to this foundational problem lies in evolving a simple recurrent neural network. This brings us to the more sophisticated architecture called the LSTM, which stands for Long Short-Term Memory Network, and a gated recurrent unit or GRU. The key to the simple RNN is how it calculates the new hidden state based on the current input and the previous hidden state. The calculation begins with two critical inputs. First we have xt, which is the current input. This is the new word or data point the network is reading right now. Second we have ht-1, which is the previous hidden state. This is the network's entire memory from the step just before this one. The current input xt is multiplied by its corresponding weight matrix, which is WIH, weight input to hidden. This converts the input into a format suitable for the hidden state. The previous memory ht-1 is multiplied by its matrix WHH, which is weight hidden to hidden. This determines how much of the old memory should be preserved. The first multiplication gives us the input contribution, which measures the influence of the current word. The second multiplication gives us the memory contribution, measuring the influence of the past. Next, we simply add these two contributions together. Finally, we include the bias term BH, which allows the system to shift the activation function. All three terms, the input, the old memory, and the bias, are combined into a single comprehensive sum. Now we move on to the final step to generate the new memory. This sum is passed into a tanh activation function, which is the hyperbolic tangent function which sequences the combined value into a range between -1 and +1. This nonlinearity is essential for the network to learn complex relationships. The output of the tanh function is our final result, which is the new hidden state ht. The single vector represents the network's update understanding of everything it has seen up to this point, and it is passed as the new memory to the very next cell in the sequence. And that's it. The RNN's genius lies in this recursive loop, combining the current input with the comprehensive memory of the past to produce a new informed memory for the future.